All right, before I get into more stuff on sequences and series, I wanted to go over the quiz that was due this past Saturday. Didn't get some of the high scores that I'm used to. So I wanted to, and especially since it's early in this chapter and it's a long chapter, I want to make sure that we get things sorted out quickly. So let me put these side by side. All right, so this first one here, just wanted examples of the following, and there are lots of ways to answer these. I saw a lot of correct things for most of these. So let's just go through them in order. So a sequence that's monotone but not bounded. A lot of people actually had the example that I came up with. It was basically just a sub n equals n. So clearly that is not bounded. That'll get as large as possible since n is just going to keep growing, but it's constant. It's increasing everywhere. A sequence is bounded but not monotone. A lot of people also gave me the that alternating, just that indefinitely alternating sequence. I think that's actually an example we did in here. A sequence that converges but is not monotone. Lots of examples for this, but this -1 to the n over n, something we'll talk about in more detail tonight, which is sometimes called the alternating harmonic series. That is, so just know that, and I think I even mentioned this, but an alternating series is basically the furthest thing you can have from something that's monotone, because it's going to be increasing from one term to the next, and then from that term on to the next one, it's going to be decreasing, and that's going to continue indefinitely. So that's very much not a monotone series. The one on question 1 that caused a lot of problems was, I want a sequence that converges to 0, but the associated series diverges. And there are many examples. Just kind of the quintessential one is the harmonic series that we've talked about a couple different ways. We'll talk about with some other concepts today, but basically that's kind of the quintessential example of a sequence that goes to 0, but if you add up all the terms in that sequence, it will not converge to a finite sum. I saw a lot of answers here. A few people gave me like a constant sequence, like really, like for example, a sequence where all the terms are 0, which that sequence converges to 0, but the sum absolutely converges. So be careful that you're meeting all the conditions there. And then for question 2, part A is a geometric sequence, which most people did pretty well with. So if you can see the solution here on the right, if you identify the first term and the common ratio, that's really all you need to do to figure out that sum. Part B takes quite a bit more work. You have to go through the partial fractions, which I gave the hint to do. And then if you do that, you'll get this what we call a telescoping series, where really all that ends up mattering is the first term, because everything else, basically the subsequent terms annihilate each other. So all you're left with is the very first term, which is 1/2. So I wanted to go over those. First of all, before I go any further with this, does anybody have any questions about anything on that quiz? Okay, the other thing I wanted to talk about in more generality is that, I despite the extension I gave on this, there are more people than I'm used to who didn't turn this in. The homework scores today were, for a few of you, pretty low. And I understand, I know this stuff is tough. I know it's difficult, and I know that, like I said at the outset, you're taking a 16-week class. It's compressed into 6 weeks, and being halfway through it is, I'm sure a lot of you are burned out, and I understand that. I definitely don't want to trivialize that, but I also feel like I need to remind you that, you know, we got 3 more weeks of this. There's a lot of class left, and if you're going to be successful, which you all absolutely can be, yeah, please don't back up. Yeah, please don't slide backward now. You know, my office hours are typically empty. I don't have a lot of chatter on Slack. I haven't gotten many questions in my inbox. Just before we get going today, I just wanted to remind you that, you know, please reach out if you need things. I know these things are tough, but they are absolutely learnable, and I am absolutely here to help if you need with that. So please reach out if I can do anything. Another reason I bring it up is, like, I've gotten a few quizzes recently where some of you have made notes like, oh, I didn't know what this meant, and I didn't know how to do this. Yet you're turning things in more than early enough to reach out to me and get some clarity. So if I put something in an assignment or a quiz that is unclear, please ask me and I'll clear it up for you. Or if it's clear to you but you just don't know how to get started or don't know how to continue, yeah, please reach out to me or somebody else. All right, so let's go ahead and get to some new stuff. So chapter 11 is what we're dealing with, all about sequences and series. We're on section 3 now. So the next few sections are basically more of these tests that, you know, basically more of these tools to help us figure out what these series do. So section 3 is all about the integral tests. So let's get a couple of examples we already know about, and then we'll use those as the jumping off point to look at some new series. So this guy here, does this series converge?
Yeah.
Yeah, it does. Do you remember what?
Doesn't it go to 0?
Well, I mean, the sequence does go to 0, but remember, that's not enough.
Oh yeah.
And actually, now that I'm asking how we know this converges, maybe we haven't. I don't know if I've given that specific detail to a specific test yet. So beyond that, so we know it converges. Now I can't remember how I've justified it, because we're definitely going to put more justification behind it now. But now what we want to do, we want to approximate its sum. So let's do this. I'm going to draw a graph of, you know, the first few terms in this series. So let's do 1, 2, 3, 4, 5, 6. So I know this converges. I know that so this might be my n-axis, this will be my a sub n. And we know that this, basically the largest term here is going to be the first term. 1 over 1 squared is 1. So then the next term is going to be 1 over 4. So let's put some hash marks in here. Second term is going to be 1/4, then 1/8, no, 1/9, then 1/16. Basically, this is going to be, you know, cascading downwards. So if I keep saying that these are not continuous functions, these are only defined integers, but what if we replace this with something that is defined everywhere? So defined on all real numbers, and specifically from 1 onwards. So we're looking at this series from n equals 1, and then n increases without bound. So with continuous functions, we can join these points with a curve. Basically, and we know as n approaches infinity, the function is going to approach 0. So something I want to do here is I want to think about these as areas, which is something we've done before many, many times. So the way I want to try to approximate this series is to think about these rectangular areas. And the way I'm going to approximate these rectangular areas is to find the area under this curve. So how can I find the area under this curve?
I mean, do you want us to use integration or?
Yeah. So yeah, I mean, basically what I'm doing is this. What I really am interested in is the sum of the areas of these rectangles, but the way I'm going to get there is by, I want to do an integral. So I'm going to integrate from 1 to infinity this function, x to the -2 dx. So that's an improper integral, so I really need to set that up as a limit. So limit as t approaches infinity of and as the limit, as t approaches infinity, -1/t will vanish, it will go to 0. So this limit is equal to 1. So I got that this area is equal to 1. Does that mean that the sum of this series is equal to 1?
Yeah.
So be careful with that, because look, see these rectangles that I drew in here? The rectangles here are actually what the sum of the series is. But when I did this integral, what did I actually find?
The area under the curve.
The area under the curve, which includes all this stuff too. So what do I know then about this sum?
It'd
Based
be
on
less
that
than
value of
1.
the integral. Oh, sorry, Jacob, go ahead.
Would it be less than 1?
Yeah, we know it's less than 1. So this integral here, how does this integral justify what I said at the outset here? How does that integral prove that this series converges?
But shouldn't the sigma and the integral shouldn't be the same, right? Because the integral is sort of like the area. And
Yeah, I
the
mean, I'm not saying they should be the same. Yeah, they're not going to be identical, because typically when we do an integral, what an integral really does is it takes these rectangular areas and it makes them infinitely narrow. But we don't want to do that with a series. With a series, we are only looking at basically I'm only looking at this function when x has integer values, so x equals 1, x equals 2, and so on. So when I'm taking the sum of a series, I'm not trying to set up that limiting case. So the integral does not give me the exact value of the series, but it does give me an upper bound. I know that the sum of this series is less than 1. So again, why does this integral, why can I use this integral as proof, as justification that this series converges?
Because the integral itself converges and it's less than 1. The series is less than 1 because you're only taking part of the area under the curve.
So basically, yeah, and you're right on. So basically, think of this integral as my worst case scenario. Basically, if I was going to take all that area, would it converge? In this case, it does. But in reality, I'm only interested in a portion of that. I mean, no matter how big that portion is, I know it's going to converge.
But Professor, I have a doubt.
Yeah, go ahead.
I'm sorry. So if you're sort of like thinking about like f of f of you're not adding f of x dx, right? You're adding f of x, like f of x, f of 1, f of 2, f of 3, f
Well,
of 4.
but it's yes, but it's the same thing as finding the area, because how wide are all these little intervals here?
One.
Those are all 1 wide, right? So to find the area, what I'm really doing is I'm multiplying f of 1 times 1 plus f of 2 times 1 plus f of 3 times 1. So you're right that really I'm just adding f of 1 plus f of 2 plus f of 3, but what's hidden in that is that I am multiplying by the width. I'm multiplying height by width to get proper areas.
But I'm sorry, like okay, so okay, got it. So
Okay, you
you're,
sure?
yeah, I'm sure, but because I was a bit confused, like, you know, because if you're gonna add f of 1 like that, it'd be a huge number, right? Like, oh, okay, so I think I'm having a mistake here, because I think I'm taking a function of like a real number instead of a natural number, like f of 1.1 and all that. Maybe that's
Oh, right. So yeah, I mean, the integral does, yeah, the integral does not deal with these intervals that are, these subintervals that are 1 unit wide. The integral is the limiting case here. So one more note I'll put in here is, so this integral, I'll just call it f of x dx in general. No, that is equal to, and what's the right way for me to,
so it's like a Riemann sum.
it's absolute, it's not like a Riemann sum, it is a Riemann sum. And basically, so this sequence or this series that I'm dealing with, I'm not trying to make the intervals any narrow, any smaller than one unit in width, but basically what the integral is doing is basically limiting this. And I should have put this in here, but I'll kind of squeeze it in here. The limit as n, you know, I'm going to hold off on this. I don't want to mess up the notation. So I'll add that backwards, or add the notation in after the fact. But really, yeah, the integral is finding the areas of those rectangles, but I'm trying to find the limit as the rectangles get infinitely narrow. Where with the series, I'm not trying to do that. So in this case, we're using an integral to justify that series converges. So let's look at this one now. So I have this, the series, or the sequence is 1 over square root of n. And maybe we haven't talked about this one before, but does this one converge?
No, I mean, it's just,
So I'm going to say you're correct and no, and I don't remember if we've talked about this specific series before, but we've talked about things like it. So let's do the same thing here. I'm going to,
But it depends on how you look. I mean, how are you sort of like looking at it? So like with respect to the x-axis or like with respect to the y-axis?
well, I mean, the convergence of a series doesn't depend on that. I mean, if we just write out the first few terms of this series, this will be 1/1 plus 1/√2 plus 1/√3, and so on infinitely.
I'm talking about the perspective wise, like, you know, you have that area going on, and that's like f of 1 times 1, f of 2 times 2, and all that. But then that area, like, it's getting smaller and no, it's okay.
Yeah, the areas. So yeah, the individual areas are going to get smaller and smaller and smaller. But remember, that is not enough to say that a sequence or a series converges. In fact, we're going with this claim so far is that this does not converge. So this one, in fact, is still going to go. The sequence goes to 0, but not as rapidly as the last one did. So, you know, our first term is 1 in both of these series, or both these sequences. The second term for our previous series was 1/4. This one's going to be 1 over the square root of 2, which is around 7/10. And then 1 over radical 3, I think, is around, I think it's a little bit higher than a half. So you get, and I'm going to do the same thing where I trade my, you know, discrete sequence definition for a continuous, you know, real valued function definition that looks like this. So there's a lot of space between the curve and the x-axis this time, but hopefully you realize that as n gets very large, this curve is going to get arbitrarily close to the x-axis. The terms are going to get arbitrarily close to 0. But what I want to do here now is I still want to approximate with rectangles. And I'm sorry, this time I want to do a different approach with rectangles. Basically, I want the left end of each one of these rectangles. Basically, I want the height of these rectangles to take the left end of the curve over their interval. So in my last example, I had the basically I had some space between the rectangles and the curve. In this case, the rectangles are going to be above the curve. So let's set up an integral again. I want the integral from 1 to infinity of x to the -1/2 dx. So again, we got to set this up as a proper integral. So what is this integral going to do? I mean, I'm sure at least one of you is ahead of the work I'm doing. What's going to happen with this integral? What's going to happen is t gets very large.
Should I get to infinity?
Yep, goes to infinity. So basically what we found is the area underneath this curve. So the area underneath this curve can't be calculated. It goes to infinity. It diverges. So what does that mean about the series then?
Would it also diverge?
It also diverges because if you look at the way I drew the rectangles, you know, these areas are larger than the integral I just took. So if the integral couldn't be finitely found, then the series cannot be found either. So no.
So if you were underestimating the areas here, it would still converge.
No, not necessarily, but it also wouldn't give you any good conclusion. Because let's say I found an integral. So we know the integral diverges.
Right.
But if our integral was bigger than the actual area, the actual sum of the series we wanted to find, then maybe the series converges. We didn't do a good test in that regard. So I'll kind of draw the example here, which I sort of tripped myself up and was about to do anyway. But if I redraw the curve, and let's say I went with these rectangles, and basically I have area between the rectangles, which the rectangles are symbolizing the series. I have area between the series and the integral. So if I find out that the integral diverges, then I really can't say that the series diverges because the sum of the series is going to be smaller. So maybe it's finite. But the way we actually approach this, I know that the integral of the area to find the area under the curve diverges. So anything bigger than that is going to diverge as well. So just to, I'm gonna go back a slide to look at the contrast here. We know this series converges. So I found an area that with that integral that converges. And since my series is going to have a lesser value than that, it has to converge as well. In fact, we know that it can't be, and it can't even be as large as 1.
That makes sense, but like, aren't you getting the value of the series? Or I'm not saying this correctly. Based on your graph of the series, you can see that it's underneath the curve, and you see that the integral itself converges to 1. So like, I guess my question is, sorry, I'm not like formulating it correctly. Can you go? Yeah, can you go forward 1 slide?
Sure.
So like, I'm sorry, it's a really bad way to put it, but like, you wouldn't unexpectedly end up with this second graph here on the right, like sorry, I'm like not figuring out how like word it correctly, but
so we're gonna get to something later, not too much later. It'll be sometime tonight that kind of talks about when you, because basically the overestimate or the underestimate, that is a direct function of what we're trying to prove. So, and we'll go over later how to make that choice.
okay, yeah, I guess that's what I was confused about. Thanks.
And obviously you saw me get tripped up by it, so yeah, no worries there.
So I have a quick question.
Yeah, go ahead, Jacob.
So how is formatting the integral different between if you did the one we did in the underestimating it?
Oh, I
Like,
didn't
how
really
would you
set it
set
up
up-
any differently, did I? So if I go back to the very first one, what I should have done, I went from 1 to infinity. Oh, you know what I should have done is this. So from 1 to infinity, I got 1, right?
Yeah.
But that doesn't cover the rectangle that I drew in here at the far left.
Oh,
So really, I should have done this integral plus 1 equals 2. And therefore, that series is less than 2. So, I mean, really setting up the integral wasn't any different, but I totally neglected that far left area there.
okay.
All right, good. Thank you for catching it. All right, so the integral test, which is basically what we just went through. So here are the conditions under which it works. So you want your function to be continuous, positive, and decreasing. So pay attention to all 3 of these things, which, the functions we just dealt with were basically rational functions, or yeah, they're both rational functions. So another continuous, meaning I did not include 0 in my intervals, which is the only place where they're not defined. So they're all continuous. They're all positive. Dividing 1 by a positive number is going to give you a positive number, and they're all decreasing. So I'm okay on all 3 of those fronts there. And really, so if I have that function, then I need to have a sequence that basically the sequence that agrees with the function at all the integers. And if I have those 2 conditions met, then here's what I'm allowed to do with the integral. So, and I want to highlight one phrase in here, which, you may not know the true power of by this point in your math career. So this series converges if and only if the associated integral converges. And the reason I'm highlighting if and only if there is because that basically means those 2 things are equivalent. You can use something you know about the series to prove something about the integral, or vice versa. Another way to say this is if, and basically that's what I showed you in the second bullet, is to show that you can go both directions with this. In fact, sometimes you'll see the symbol for if and only if it looks like this. And that really means that if you have one, the other must be true. It doesn't matter which direction you're going.
I guess that was a little bit like kind of what I was asking. It was kind of like if you can tell the series converges or doesn't from the integral, like why like how would you even make the mistake of it, of underestimating it, or like not making a good choice with the sums? You know what I mean? Like,
yeah. So here's the beauty of this. If you look at the conditions of this test, nowhere in here am I even messing around with that overestimate or underestimate. If you have a continuous positive decreasing function and you have a sequence that agrees with it on every integer value in the domain, then just set up the integral in the logical way and you're fine.
thank you.
Mm-hmm. So let's use this thing here. Oh, one more bullet, I guess. Basically, if one diverges, the other diverges. If one converges, the other converges. And the really powerful thing that you might overlook because this is a brand new thing is that you can go either direction on this. All right, moving on. So now let's look at this one here. Does this thing converge? So if you want to set up the integral test, then we have then so this series is not built on a continuous function, but we can make a continuous function that mimics this. So I'll do that here. So basically, this is a continuous function that's defined for any real value of x, and it's definitely going to agree with my sequence here. So now we got to make sure that we can check off all these boxes. Positive, continuous, and decreasing. Are all three of these things going to be true?
Yes.
Yep. So positive, yeah, I am dividing 1 by a number that is going to have to be positive. Decreasing, the denominator grows while the numerator does not. And continuous, there is no real number that can make the denominator equal to 0. So it's definitely going to be defined everywhere. It's going to be continuous. All right, so I can integrate from 1 to infinity dx over x squared plus 1. Do we know this integral?
Would it just be 1?
Well,
Dx over 1. So
it's not dx over 1. It means it's so I need to integrate this function here from 1 to infinity.
oh wait, sorry. Never mind. I was doing some weird math in my head.
Okay. Do you remember the antiderivative of this?
Isn't it ln x squared plus 1?
It's not natural log because I don't have, basically to make that natural log result, I would have to have basically the derivative of x squared plus 1 multiplied by this function, which I don't. This is actually, oh, sorry, you got something, Alistair?
No, go ahead.
Okay. This is actually the arctangent of x. So limit as t approaches infinity of arctangent t minus arctangent 1. And we did it last week, maybe 2 weeks ago. Basically, let's draw a triangle here, just to kind of jog your memory. Arctangent t, so here's my angle, theta. Opposite side t, adjacent side 1. As t gets really, really large, what's going to happen to theta? What's theta going to approach?
90 degrees.
90 degrees or pi over 2. And arctangent of 1 is pi over 4. So my integral from 1 to infinity is finite. So what does that mean about my series?
It converges.
It converges. And one thing I want to point out is I know it converges. I'm not saying the sum of the series is pi over 4. It's probably a good approximation, but it is not, almost certainly not equal. Any questions on this one here? All right, moving on. And this one here, which may or may not be obvious, but this is sort of a question I've asked you before. So what values of P does this thing converge? So based on the integral test, is there something I can replace this series with that we can investigate instead?
I mean, would you just take the integral of t?
The integral of T?
Sorry, I'm like just like reaching. No, like I'm yeah. Sorry, I'm getting confused. Like confused with something
No, you're
else.
okay. So based on the integral test, I want to know if this series converges, which means I can instead look at this integral.
Greater than 1.
Right, and the answer to that is, and I'll just kind of highlight some things we did today. We did, so this is my P kind of number line here. Here's 0. We looked at 1/2 and we looked at 2. We know that it converges for 2 and it diverges for 1/2. And really, yeah, we know from previous work here that the dividing line is 1. So yes, that is true for when P is strictly greater than 1. So when P is strictly greater than 1, I know that this series converges. And when P is less than or equal to 1, this diverges. And this is a very powerful tool that you can use for, usually not by itself, but you can use it for a lot of different types of series to analyze them. And this is called the P-series test, which, you know, doesn't really warrant its own section because it is so quick and basically shows up as a result from this other test, but it's also really, really powerful because it can give you some intuition into other series. So any questions here on this? Another thing I don't want to gloss over too much is, you know, I asked you this, I feel like it was probably a couple weeks ago now, where we figured out that if you have this integral, this improper integral, it only converges for powers of P that are greater than 1. And I don't know if I hinted at the time, but basically this is a very, very important result for sequences in series. Any questions about this? All right. How about this thing here? Does this series converge? Natural log of n over n. So in order to find this out, what can I do instead? I mean, I could write out a few terms in the series. First term's going to be 0. Then natural log of 2 over 2. Then natural log of 3 over 3. So maybe that gives you some intuition on what this series is going to do, but how can I prove it?
It's just tending towards 0, right?
The sequence is tending towards 0, but remember that doesn't necessarily mean the series converges. So how can I prove one way or another about this this series?
Wait, it starts with zero and like it ends with zero. Like it's like a broken function.
It's not broken. I mean, just the first value here, natural log of 1/1.
Yeah.
That's
A
equal to
zero.
0. So I
But then
mean, that's fine.
I mean, like, and the next one is like, it's like a mountain or something, like, just,
Oh yeah.
I
So
mean,
it does, yeah, it starts off by, from here to here, it's increasing. And then from here to here, and I probably for the rest of the sequence is going to be decreasing. So
it's bounded.
I think I can, it looks like it's going to be bounded. So that's another good thing to bring up from last week. Clearly, this thing is never going to be negative. Also, I think this is probably right here, natural log of 2/2. This is the greatest term. So it sounds like it's bounded. Is it monotone?
No.
No. So we cannot prove that it converges using that argument, but it still might converge. We still might be able to use some other argument. So we're talking integral test at the moment. So let's try to set up this integral from 1 to infinity of natural log of x over x dx. Is this an integral we know how to do?
Yeah.
Okay, how do we set that up?
It'd just be t minus 1.
How'd you get that?
Like substitution.
Okay, so under u substitution, what should our u be?
Natural log of x.
Natural log of x, which means du is going to be 1 over x dx, which is really all we need. So let's deal with the indefinite integral first. So the integral from, oh no, we don't need the limits, but you have the integral of u du. That's equal to 1/2 u squared. So 1/2 times natural log of x squared. So now we're looking at this, the limit as t approaches infinity of 1/2 natural log of x squared from 1 to t. So I get 1/2 natural log of t squared minus 1/2 natural log of 1 squared. This goes to 0. So what does this mean about this? What's the limit as t goes to infinity of this integral?
Infinity.
Infinity. So what does that mean about the series?
It diverges.
It diverges.
Is there any other way, other than the integral test?
Yeah, there is. So actually, in our very next section, we're going to look at the series again with a different test. But yeah, there are other ways to see it. And that's, as I brought up a few times, it's kind of the good news and the bad news about all these sequences and series tests is that you might be working with a test that will get you the answer that you need, but it might not be the most efficient. So yeah, we'll do lots of practice to, to kind of help you with your decision-making process.
I mean, one way I sort of like look at it is like, if you're gonna cross multiply everything, it's just gonna be n factorial, n factorial times natural log of 2, n factorial natural log of 3, all that divided by
You're saying n factorial times natural log of n?
but like if you cross multiply everything, n factorial by like that, n factorial by, yeah, like that, n factorial by 2, n factorial by by 3, and like that, we keep on going. Like,
I guess I'm not seeing. So when you say you're cross multiplying, are
yeah,
you basically saying you're gonna multiply both sides of this?
can I annotate?
Yeah, absolutely, go for it.
So yeah, what I was trying to say is like, this by this, and this by this, and like it's gonna keep on going, right? So
Mhm.
like you have 1/3 plus 1/2. That's like any cross multiply, you get 2 plus 3 by 6. So when you do the same thing for this, it's like a lot of terms, like 4, 5,
Yeah, I got
6,
you.
like that.
Mhm.
So that's gonna be here. That's gonna be like n factorial by divided by 2 factorial, and that term natural log of 2 by that this is just a constant, I don't know, and then that you have n factorial by that's not 3, some value, and it keeps on going.
Okay.
But that bottom one would always be lesser than the top one.
Right. That's a clever way to look at it. But it might be a little hard to write out and justify. So the integral test is probably a little more straightforward. There are other ways that I'll show you actually pretty soon. But yeah, I mean, kind of even going through that is valuable because it gives you some insight as to what the actual answer is, because most of the time I'm not going to ask you, all right, prove that this series diverges. I'm going to ask you what it does and for you to justify it. So the smaller but probably first part of the battle is figuring out how the sequence behaves. All right, and that was all for the integral test. I'll back up a slide just to pause for questions again. Anybody have any questions about the integral tests, when you're allowed to use it, how it works? Okay, so let's move on to section 4 then. Keep the annotations. All right, so a couple more tests that are also very powerful that I want to talk about are the comparison tests. So to talk about these tests, let's look at a couple examples that we might not be able to prove what these things do, but we probably have some intuition about them. So I have 1/2 to the n plus 1. What do we think? Does this thing converge or diverge? So whether or not you can prove it right now, what does your gut tell you about what this series does?
Converge.
Okay, I got 1 vote for converge. Anybody want to second that or vote for no? So why do we think that it converges? What gives us that idea?
I I I approximated it to be 1 by 2 raised to n.
Okay, so I'm hoping that I can think of this as 1 over 2 to the n. This definitely converges. How do I know that this thing converges? What's the very quick answer you can give me to prove that you know this converges?
Oh, that's just 1 over 2. It's a geometric series. The
So as a
ratio.
geometric series, that's almost enough.
With the common ratio less than 1.
With common ratio equal to 1/2, which is less than 1. So yes, I know that I know the series of associated with 1 over 2 to the n converges, because that's a geometric series. But here's the bad news: 1 over 2 to the n plus 1 is not geometric. So if there's some kind of way I can use what I know about this geometric series to justify what I think I know
You
about
can
this new series,
you can make it 1 over 2 raised to n plus 2. That would be 2 raised to n plus 1. That would be 1 over. Yeah.
so you're saying 1 over 2 to the n plus 1,
2 to the n plus 2.
right? But even then you are, so are you saying this is geometric?
Because that's gonna be 1 over 2 raised to n plus 1. And yeah,
So
the
this right
next.
here is not true.
Oh, no, no, no. Fuck, come on, what the hell?
Okay, that's okay. So I like that you're thinking about it, but the bad news is that the series I gave you is not geometric. So for the moment, and it's really only for the moment, I cannot make any justification about that. So that's kind of what I'm using this to motivate. So how about this one? Does this thing converge? What do we think?
Wouldn't the first term make the denominator 0?
Yes, it would. Good catch. So let's do this. Let's say it starts at n equals 2. So now the question can actually be asked. Does this series converge? And just remember, I don't think right now there's any way you could know for sure. That's really what I'm trying to build up to. But do you have any kind of intuition or any?
I mean, it feels intuitively like it diverges.
Okay. And what gives you that intuition, Rias?
Because I don't know if this is, it seems right. It's like, I mean, I'm sort of like viewing viewing the sequence like, it's like 1 over, if it's 1 over n, it's like 1, and then you have 1 over half, that's 0.5. And if you're just gonna subtract n minus 1, that's going, it's like you're sort of like slowing things down.
Yeah. So you're on the right track to kind of bring these things together. So now let's formalize why I'm kind of building up to this. So the first test in this section we're talking about is the direct comparison test. So a couple of conditions here. So I have 2 different series, and you kind of saw that with the way I walked through those, or the way you kind of walked through those other 2 series. I gave you a series that you don't really know anything about. So if you can bring in some other series that you absolutely know that it converges or diverges, if I can have some kind of interaction between those two things, that would be valuable. So I have two series with positive terms. And here's the test, basically. If one series converges and the other is basically all the terms are less, all the corresponding terms in the other series are less, then the quote unquote smaller one converges. And the other side of this is if you, and I'll kind of put this in here, let's say this is a known series, and this A sub n is a, you know, I'll call it the series of interest. Probably the one I asked you about. So really, if I can bring in this known series, which is probably simpler, then I can use it to make these conclusions about my series of interest. So if I have a series that converges, and let's think back to the integral test about, you know, if I have this integral that converges and my series is actually going to have a smaller sum, then that smaller sum is also going to converge. That's really the same rationale for that top bullet there. If the series Bn converges and my series of and my sequence A, all the corresponding terms are going to be less than they are in the corresponding sequence for B, then the series for A sub n has to converge as well. On the other hand, if my known series diverges and all the terms in my sequence of interest are bigger than the known sequence, then it has to diverge as well. That series has to diverge as well. So any questions on the logic, the setup of this direct comparison test so far? All right, so in fact, now that we've done that, let's go back a few slides and let's just kind of fill in the details. So we would like to compare this with 1 over 2 to the n plus 1. So I was thinking, or somebody was thinking, that this thing converges. So how do I want this to be related to the 1 over 2 to the n?
Actually, there's another way of looking at it.
How's that?
You know, it's sort of like, you know, it's like you have 5 squared plus 1, but 5 squared is 25, and 5 squared plus 1 is 26. So it should be 5 raised to 2 point something. Like
right.
it's so 2 raised to n plus 1, it should be like 2 raised to n plus a constant. And
I don't think you're going to get a constant.
or no, some value, like it's changing, but it's still some value, like, you know.
Right. So you're absolutely right. I don't think there's any way you're going to find a constant that will work for the entire series, the entire sequence, but you don't actually need that, because first of all, are we okay with this being true? Why can I say that 1 over 2 to the n plus 1 is less than 1 over 2 to the n? So let's look at what that comparison test told us. I know, we already talked about why, that 1 over the series of 1 over 2 to the n converges. So that means that the series from 1 to infinity of 1 over 2 to the n plus 1 converges as well. So I guess the last blank to fill in here is, why can I say this? Why is this inequality true? Why is 1 over 2 to the n plus 1 definitely less than 1 over 2 to the n?
Is it because the denominator is bigger?
It's because the denominator is bigger. The denominator is bigger and the numerator is constant. So basically, here are the two pieces of evidence that I need. I need this inequality. That's one. And I need to be able to justify that this geometric series converges, which we did previously. All right.
So, real quick question. So
Go
if
ahead,
1 over 2 to the n, if that, let's say that was something that diverged,
Mhm.
would that mean we couldn't use this rule?
So if you have a sequence that diverges, and basically, why don't you hold that question? Let's do this other example, and then I'll get back to you, Jacob, because I think going through this one as well will clear that up. So we believe that this series that I gave you diverges, and we were thinking we could compare it with 1 over n. So I really want to know about 1 over n minus 1. So if I want to compare it to 1 over n, so this thing right here definitely diverges. So if I want to prove that 1 over n minus 1, this series diverges, how do these sequences need to be related to each other? How does 1 over n minus 1 need to be related to 1 over n?
It needs to be larger.
It needs to be larger. And is that true? Is the left larger than the right in this case?
Yeah.
For the same reason, the denominator is smaller on the left. So here's my first piece of evidence. I have a known series that diverges, and I have the series I'm trying to gather evidence about. That sequence is even larger. So that means that I gotta remember to keep my indexes straight since I messed up there. Since this diverges, this bigger one diverges as well. So Jacob, back to your question. It is all a matter of what you're trying to prove. So if you have a known series that diverges, or a known sequence, basically the test sequence you're trying to bring in, you know that one diverges. But the other thing you're trying to show is less than that, then you can't show me anything.
Okay,
And
that makes sense.
I'll give you an example here. I could definitely tell you this. 1 over n squared is less than 1 over n. But I could not use this as a proof because this thing diverges. So but 1 over n squared being less than that does not, I can't draw any conclusion from that.
Okay, that makes sense.
So this slide we went through. So let's talk about this one now. So this is a nasty looking series. There's a lot of stuff going on. But hopefully now we can quickly justify whether it converges or diverges. So first of all, what do we think? Does it converge or diverge?
Go converge.
Yeah, I mean, we have a pretty good idea that it converges, and I'll tell you right now that it does. But how can we prove that? So this is our, just to use the language that we've introduced, this is our series of interest. What is a good known series that we can bring in and compare this to?
Would 1 over x squared plus x work?
So I'm hearing 1 over n squared plus n. So that's a good start. It's definitely simpler. But 1 over n squared plus n is not really, not a series I could tell you something about very easily. So is there something a little simpler could I even drill down a little further and give us something even simpler?
Just 1 over n squared.
Yeah, let's just try to get to, if we can get to 1 over n squared, I can definitely make some assertions there. So let's use that middle step there. And basically what I'm trying to do, let's be really specific about this one here. Build it up slowly. I know that this is going to be true. Can I say that this is going to be true? Is the denominator, or is the denominator 2n squared plus 4n always going to be bigger than 2n squared?
Yeah.
Yeah. And then I think with our last move here, we can say that this is less than n squared. Does this series 1 over n squared converge?
Yeah.
Yes. And why do we know that is true?
One. I think there's another way of looking at it, but it's like I don't know if it's valid because like you have a geometric series which is like when r is less than 1, it's it's converging. So 1 over n squared is like 1 over n the whole square.
So that is not geometric, and I think you're getting
no, it's not geometric. But the thing is that when like all the 1 over n's that are like in the sequence, right? Like when you have the sums,
Mhm.
like 1 over n, you have 1 over the next 1 over n, like and all that. That's all less than 1. So by it's so the sum should be converging.
So a couple things about that. If you're going to start comparing with a geometric series, you really need to have a series that is geometric. In this case, it's not going to be. The other thing, it sounds like you might be able to justify that the sequence goes to 0, but that is not enough to tell me that the series converges. So I'm not saying there isn't something.
Oh, the integral test. Yeah. The integral.
Yeah, I mean, and this integral might get out of hand pretty quickly. But this direct comparison test should be more straightforward. So back to this 1 over n squared. How can I justify that this sequence converges? What What argument can I make?
P-series test.
Yep, this converges by p-series because p is greater than, no, not the order I want to say. P is equal to 2, which is greater than 1. So, and I've already showed that my sequence of interest is less than this sequence I just talked about. So that means this series we just talked about converges as well. Any questions there? Okay, let's look at another one. So hopefully this series looks familiar. We just looked at it with the integral test. We use the integral test to prove that it diverges. So now we want to use the comparison test to show that it diverges. So in order to do that, I need to bring in a series that I know something about. So what's another series here that I can look at to help me?
Would you do 1 over k?
Let's think about 1 over k. So let's look at a few terms here. So this one here, we already kind of looked at the first two terms here. It's going to be natural log of 1 over 1, which is 0, plus natural log of 2 over 2, plus natural log of 3 over 3, and so forth. This guy is going to be 1 plus 1 over 2, plus 1 over 3, plus 1 over 4, and so on. So I am trying to show that this natural log of k over k diverges. So what do I need to be able to say about, if I'm going to use 1 over k, what needs to be the relationship between these two series to prove that this one diverges?
That natural log k over k is bigger.
Okay, so natural log of k over k is larger than 1 over k. Is this true?
No.
So it's not true for all k, but it is true. So let me put some details here. Natural log of 1 over 1 is less than 1 over 1, clearly. Natural log of 2 over 2 is less than 1 over 2, but natural log of 3 over 3 is greater than 1 over 3. And hopefully it's clear that, you know, the natural log of any number 3 or greater is going to be bigger than 1. So while this is not true for all k, this is true for all k greater than or equal to 3. And that's enough, because if you think about the way convergence, the way we figure out convergence or divergence, it's really all about what happens as k gets very, very large. So since this inequality is true for an infinite amount, an infinite number of values of k, then it's not really going to matter if the first couple of values, this isn't true. Because it's going to be, this inequality holds for an infinite number of terms. So just to be really thorough, how do I know that this diverges? Hopefully one of you is thinking this. Diverges by p-series test. P equals 1. And this inequality here shows that natural log of k over k diverges. And just to kind of make one more note here. Let's say I had k equals 3 here. If I start this sequence at k equals 3, then yes, I can say this inequality that I wrote above here, that inequality is true for every k. So if that diverges from 3 to infinity, then it's going to also diverge from 1 to infinity. Those two other terms aren't going to make it converge. Any questions here? All right, let's move on. How about this one? 1 over n squared minus 1. Do we think that converges?
Yes.
Okay, so it's okay. I mean, don't really know yet, but we're gonna say yes. Colin, why do you think it does? Is there another series you're thinking about?
I was thinking of 1 over n squared.
Okay. Now, can we use our direct comparison test with 1 over n squared? So if we try to set this up, we know that 1 over n squared, that series converges. So we need 1 over n squared minus 1 to be less than that. But is it? And same problem as before. I got to change the indices. Is this inequality true?
No.
No. So the direct comparison test will not help us, at least not with 1 over n squared. So we need a different tool. So I'll make a note here, direct comparison fails. So we need another tool to help us prove this, because this is true. This series converges. So we just can't prove it with this test. So we got to bring in something else. And that's called the limit comparison test. So first test, I'm just comparing these sequences directly. The limit comparison test, I can't compare them directly because it doesn't help, but I can compare their respective limits. So same conditions. I have to have 2 sequences or 2 series whose sequences have positive terms. I guess same drills before. One of those is a known series. The other one is a series I'm trying to learn something about. And I'm going to find this limit. I'm going to find the limit of their quotient as n goes to infinity. And I really need to make this, stress this right here. My limit needs to be positive. So when I find the limit of this quotient here, my limit needs to be positive. So I'm going to say this really explicitly over here, not 0. So if you meet those 2 conditions, then here's what the limit comparison test tells you. Either both series converge or both series diverge. So bringing in that known series, basically, if you can show that their limit is a positive number when you basically take the ratio of those sequences, then you know that both of those series have the same behavior. They either both converge or both diverge. So back to this one here. Colin had the idea of comparing this to 1 over n squared, but the direct comparison test wouldn't help us because the inequality goes the opposite direction that would help us. So what I would like to do is find this limit, 1 over n squared minus 1 over 1 over n squared. So then I get the limit as n approaches infinity of n squared over n squared minus 1. And what is this limit? So that limit is equal to 1, which is positive. So I know this here converges by P series. The limit of their quotient is positive and real. So that means this converges too. Any questions here?
But Professor, if it converges to like 1, wouldn't it be like big numbers, like, you know, like, you understand, like,
So the limit, that limit 1, that's as if that only comes from me taking that limit comes from me basically taking the ratio of these two sequences,
oh, okay, gotcha.
not either one of them individually.
Yeah, sure.
Yeah, so it's a good point, a good thing to bring up. Anything else about this example? Right. How about this one here? Do we think this converges?
Yes.
Got to vote for yes. And why do you think that's the case?
The comparison.
What are we comparing with?
P raised to n. Oh, well, sorry, 2 raised to n. I guess.
Yeah. I think you meant 1 over 2 to the n, but yeah, that's a good thing to compare it to. So if I compare this with 1 over 2 to the n, I know this thing converges by geometric series. With common ratio equal to 1/2. So can I use the direct comparison to help me in this case?
Yeah.
So if I have 1 over 2 to the n minus 20 and 1 over 2 to the n, so I would need this to be true. Which I don't believe is true, since the denominators on the left are going to be smaller. So in this case, direct comparison won't work. So let's try limit comparison. So your turn now. If I want to do limit comparison, how do I set that up?
Would it be the limit of 1 over 2n minus 20 all over 1 over 2n?
Yep. And I don't remember which direction I put this in the slide explain this test, but maybe you've already had this thought, but really I could look at this limit or I could look at this limit. Because we just need that, we just basically, we want our terms to be positive. And we want our limit to be positive. So, okay, let's look at both of these and hopefully that'll illustrate why it does not matter which way we do this. So I got 2 to the n over 2 to the n minus 20. And this one's going to be 2 to the n minus 20 over 2 to the n. And really, hopefully it's, see that both these go to 1. So because of that, we have a positive limit. So that means the series I cared about, even though it is not geometric, I can use this geometric series to help me prove that it converges. By limit comparison.
Why doesn't the direct comparison work? Like, it's like it.
So direct comparison doesn't work because this inequality doesn't go the way that I need it to. So I know that 1 over 2 to the n converges, but the sequence, the sequence I am trying to learn about, all of its terms are going to be larger. So as the same kind, I'll bring this example back in. If I have 1 over n, basically 1 over n is going to be greater than 1 over n squared. The one on the right converges, the one on the left diverges. So if you want to use direct,
so you're, it's like you're trying to prove it that 2 raised to n minus 20 converges, but then that term itself is greater than 1 raised to, so it's like assuming that 2 raised to n minus 20 is converging, right?
Yeah, so if I have something convergent, then I need to show that the other thing is less than that, because then that must converge. If it's larger, then it might converge and it might diverge. I haven't really, I don't have a conclusion I can make. Any questions? Any other questions on this example?
Thank you, Professor.
Oh, no problem. Thank you. All right, and that was the last one. So let's go ahead and finish this one here and we'll take a break. So kind of a nasty thing here. I'll let you take a look at it for a bit. Do we think this thing will converge?
No.
Okay, I got to vote for no. What other series were you looking at, Jacob, or were you thinking about?
I was kind of thinking about the 1 over square root n.
Okay.
So now I'm not too positive if that converged or diverged. Yeah,
Oh,
that
so
diverged.
yeah, 1 over radical n. This diverges. How come?
Because of the integral test.
Integral test is one way. Yeah, one way we showed it. Probably the
P-series.
more straightforward way is by p-series test, because p is equal to 1/2, which is less than 1. I'll say less than or equal to 1 because that really is what makes the p-test fail. So is that a good series to compare this to? I have 2n squared plus 3n. Let's think about it this way. What's the highest power of n in the numerator?
2.
What's that? 2. What is the highest power of n in the denominator?
5/2.
Yeah, 5 over 2. So 2, that n basically n squared over n to the 5 over 2. So I think this is a good candidate for some comparison test. Could we use direct comparison test? So let's say this. I know basically my goal would be this: 2n squared plus 3n over radical 5 plus n to the 5th. Actually, you tell me what the goal is. I am trying to show that this thing I gave you diverges. So which one of these series or which one of these sequences do I need to be larger? The one on the left or the one on the right?
One on the left.
One on the left. So I have one sequence whose series diverges. So the only way to show that something else diverges is to show that it's larger. So now let's give ourselves some room. And I set up like a string of inequalities that show that the one on the left is always greater than one on the right. So I think I could definitely do this. So I think I could definitely go that far, but then I think I'm kind of stuck because if I try to go any further, then I might start saying things that are not necessarily true. Actually, I think I'm already. Yeah, I think the direct comparison is not going to get me to where I want to go.
I mean, but you get square root of n, but then you split it, you get square 1 over square root of n cubed, right? So that, yeah, that.
But if I
isn't
split
that-
them up, I'm still going to have to add them together. I'm still going to have to add the series together.
Oh yeah. So like if it's but if it wasn't it like if it's converging and converging the term, the added term should also converge.
Yeah, if the individual series converge, then then their sum converges as well. But I'm trying to show divergence because that's what I suspect. So direct comparison might work. It's getting a little bit difficult. So I'm going to try limit comparison instead. And very rarely is there only one way that these can be shown. I just think limit comparison based on what we're given might be a little more straightforward. If you disagree and can find it some other way, that's awesome. I'm going to go limit comparison this time. So I'm going to find this limit, 2n squared plus 3n over square root of 5 plus n squared, all over 1 over radical n. So that'll make this 2 times n to the 5 over 2 plus 3 times n to the 3 over 2 over 5 plus n squared to the all right. So what can I do with this limit?
I think you can also do a like a see 1 over n diverges.
1 over n?
Yeah, no, it's just what I'm trying to say. It's like 1 over n diverges, but then like you have one n which also diverges. It's like n square, or how do I n square over n also diverges. So it's like like, so there's like some sort of p series stuff going on there, like the numerator, like there's like a strict bound, like after which it's sort of like diverges or converges.
Yeah, again, I think there might be something there. I'm not sure. It might be hard for you to get to the finish line that way. I'm not seeing the end, and that doesn't mean that you can't get to the end. I'm having a hard time seeing. Maybe I'm having a hard time seeing what you're describing. So from here, just in the interest of time, I will say this limit is equal to 2, which I'll let you work through if you're not convinced, but that limit is equal to. So what does that mean for me? Well, I found a positive limit, a positive real limit, and I know that I brought in a series whose limit doesn't exist, that diverges. So that means that this series that I cared about diverges as well. By limit comparison. With this. Any questions on anything here? All right, let's go ahead and take a break. I have 7:54 and we'll come back at 8:04.
Professor, before we go,
Yeah.
The next exam is on June 16th, right?
June 16th. Yeah, that's correct.
Oh. The finals are gonna be out of 100.
Yeah, I mean, I don't know exactly how many points are going to be on the final, but it is worth I can't remember what I said now. What's in the syllabus? I think I said 40%.
It
Oh,
says
no, 30%. That's right. The midterms
Yeah.
were 40. All right, welcome back. Let's go ahead and get back in our next section here. So our next section, we're talking more about alternating series. So let's start off with a couple of series. Very similar. Hopefully you know something about the first one there. Do these series converge or diverge? How about that first one?
Converge.
The top
Or
one here?
diverge, sorry.
Yeah, the top one diverges. And the one on the bottom there, I don't know if we've talked about it much, but what do we think about this bottom one?
Converges.
Yeah, and I think I used that as an example when I was going over the solutions to the most recent quiz, but yeah, that bottom one converges. So let me share something else. So let me go ahead and take this off for a second. So we look at this graph down below here. Basically, I'm showing you two things. I am looking at the harmonic sequence here. So all the blue dots there are basically, I'm graphing 1 over k. So it's just taking the reciprocal of all those values to get those blue dots. The red dots are the sequence of partial sums. So this black dot here, the first partial sum is equal to the first term. So that's 1, and then 1 plus 1 over 2, 1 plus 1 over 2 plus 1 over 3, and so on. So the red dots, and kind of as you hopefully expect, if we look at the sequence of partial sums, there is no finite value that these are kind of trending towards. If I were to, I have this, I'm looking at the first 100 terms and the first 100 partial sums. You can kind of see that that's not going to converge to a value. But what happens if I, instead of making this equal to just 1 over k, I alternate the terms? So now what I have is this. Now to zoom in a little bit. Blue still shows the terms in the sequence. Now they're alternating. But now if you look at the red terms, the partial sums, hopefully it's more clear that those do settle in on some value. So they're going to alternate, but they're alternating back and forth, but they're also diminishing. They're getting closer and closer to some finite value. Not terribly important what that finite value is, but we do know that it converges to something. So let's talk about why. So why does, based on the kind of the graph we just looked at, why does this top series diverge while the bottom series converges? Why does alternating make that difference? Any ideas why one would converge and the other one would not?
Yeah. I think I know why, but
Okay.
I don't know. It's like when you have 1 over n, everything is just adding up, right?
Mhm.
And we have that whole explanation that the terms add up together to make half.
Yep.
And half gives you like 1. But then now you're shifting those terms with like a negative term. So now you have like something which is like way more smaller than half. That wouldn't be 1.
Right.
Half and half, one. Now you don't have a half and half. It's like something smaller.
Right.
That's just propagates throughout the series, and everything becomes like very very small values and converges.
Right. And yeah, and that's exactly right. Since essentially half of your terms in that second sequence there are negative. So adding all those things up is not going to run away. It's not going to increase unbounded the way that the harmonic series does. So every test we've talked about so far basically deals with positive series that are based on sequences that have positive terms. So this one is different. This one is all about alternating series. So few conditions to use these tests, and I've given you a lot of tests so far for analyzing series, and I want to emphasize again, I don't think maybe I haven't emphasized it enough, but if you're going to use these tests, you really need to verify that you're meeting your checklist of criteria that even allow you to use these tests. For example, if we just looked at the direct comparison, limit comparison tests, you cannot use those with alternating series because one of the conditions there is that I need all my terms to be non-negative. So you absolutely cannot use it for an alternating series test. So just heads up, definitely look to make sure all your conditions are being met. So all of your alternating series are going to look like this. Basically, I am taking the infinite sum of these two sequences multiplied by each other, a sub n and b sub n. A sub n is basically some alternating component, and it usually looks like -1 raised to some power. So if a sub n is your alternating component, b sub n is a non-alternating component. And really most of the conditions are around just the non-alternating part of this product. All the terms in b sub n have to be positive. And for all n, not sure why it says n greater than k, but for all n, b sub n plus 1 has to be less than or equal to b sub n, or in other words, b sub n is a decreasing sequence. So hopefully that looks familiar with some of the other tests we've talked about. So with the other series we've looked at, they're all positive. They're all series that are built on sequences whose terms are positive, and we have these kind of conditions for most of those. The terms are positive, but they are decreasing. And even though we have alternating sequences here, basically we're holding the non-alternating part of those sequences to the same standard. The terms are positive and they're decreasing. And basically the test is this. Not sure why I left this off here, but if all these conditions are met, then really what you have is this. If b sub n goes to 0, then this series converges. And one thing I want to make really clear here is the limit as n approaches infinity of b sub n, if that limit is equal to 0, I am only looking at the sequence. Which finding the limit of a sequence is a much easier task than finding the limit of a series. In fact, most series, so think back to what we've done tonight, we really only have the tools to figure out if a series converges or diverges. Finding the sum is usually difficult. But sequences, we can easily, more easily, find the limit of a sequence. So if all these conditions are met, then really all you're doing is you're looking at the limit of the non-alternating. component. So any questions on this test so far? All right, so let's look at an example here. So based on this, we really, you know, even though it's not a proof, like a picture, a graph is never enough to prove something, but it's usually a good tool to get you kind of get some knowledge or get some insight into something. But we have a good idea that this series converges. So let's now talk about why. So this series certainly has it has an alternating component, it's -1 to the n, and has a non-alternating component, which is 1 over n. So we need to look at b sub n. Is it positive? Is it decreasing? And hopefully we can see that if I divide 1 by a sequence of positive numbers, those are all going to be positive. Also, as n gets larger and larger, dividing 1 by larger and larger numbers is going to yield smaller and smaller decreasing numbers. So I have met both conditions for the alternating series test. So all I really need to know is this: what is the limit as n approaches infinity of b sub n? And we've taken this limit a few times, so we know very well that this limit is 0. So because that limit is 0, we have this alternating series must converge by the alternating series test. Any questions on this first one? Okay. Let's look at another one. So this series here, does it converge or diverge? So let's answer that question first. Does this series converge or diverge?
Does it converge?
Let's find out. So got to vote for converge.
I know that if it didn't have the alternating series, it would converge, right?
Let's see. So that's always a good thing to look at. So let's compare it to things we understand, or things that are at least a little simpler. So if I took out the alternating component, 3n over 4n minus 1, does this series that I've just written, does this converge or diverge?
Yeah.
Yes to it. I said converge or diverge. What does it do?
No. It diverges.
Why does it diverge?
Because when you take the limit, you get 0.75.
Yeah. So let's put it off to the side. Maybe that'll be helpful for us. The limit as n approaches infinity of 3n over 4n minus 1 is equal to 3/4. Does that change our thinking about the alternating series?
Yeah, because now that you have a an alternating value. So we can assume that it becomes plus or minus 3 less than 3/4.
Right. So basically, now what we have is, I don't want to say it's a limit because the limit is not really going to exist, but as n goes to infinity, you're going to have this behavior. This series is going to look like this: 3/4, minus 3/4, plus 3/4, minus 3/4. So because of that, I wouldn't expect the sum to converge or diverge. It's just going to alternate back and forth, with each successive term. But let's use this alternating series test anyway. So first, let's make sure we understand what we have here. I know that I have an alternating component, which is equal to -1 to the n. And I have a non-alternating component, which is 3n over 4n minus 1. Now, let's make sure we can check both of our boxes. Is it positive? And is it decreasing?
It's not positive.
It,
No,
are you
no,
sure?
no, it's positive. It's
Yeah,
positive.
it should be positive. So yeah, that -1 is not going to make it's not going to give me any negative terms. Is it decreasing?
Yeah.
Yeah, it's decreasing as well. Something you might notice is it might not be decreasing for all n, but it will. And
It would eventually.
That's kind of a good way to describe it. It eventually is decreasing monotonically. You're going to have, and this is a kind of an informal way to talk about sequences and series, but it's all about the quote unquote tail of the sequence or series. It's not totally irrelevant, but it's far more important what happens as n gets very large. That's far more important than what happens when n is, basically when the sequence is at the beginning. So it really is all about the tail of the sequence. And for some value of n early on, for every n after that, it's going to be decreasing. So I can use the alternating series test. So, and we already did it. Where we took the limit of this non-alternating part, and it's equal to 3/4. So that means that, and really, if you think about it, I don't even really need the alternating series test to bail me out here. Because is there anything I can say about this? The limit as n approaches infinity of -1 to the n, basically the sequence. Is there anything I know about this sequence? The limit of this sequence as n goes to infinity?
I don't know if you could apply the limit.
Yeah, it doesn't exist. So the limit of the sequence does not exist. So then what does that mean about the series? If the limit of the sequence does not exist, what does that mean about the series?
It's discontinuous. I don't know. Wait.
So it diverges.
Yeah, diverges. But what is it because you cannot calculate that or
yeah, it can't be computed. It's never going to settle to, you're not going to get a number out of it. But by what test or theorem? And just to, I want to make sure we haven't forgotten about it, we can say that this diverges by the divergence theorem. And let me ask you all first, do we remember what this theorem says? So just a reminder then, if a series converges, then what must be true about this limit that I'm about to write? What has to be true about that limit?
Limit a L or some.
So I should,
Okay,
the limit,
zero. Zero.
yeah, the limit exists, but it better be zero. Because, and I'll write it the other way too. If the limit as n approaches infinity of a sub n is not equal to zero, then this series has no chance to converge. It diverges. So I'll kind of phrase this the way I did before. Remember, a series is really, I am taking the sequence and I'm adding up all its terms, an infinite number of terms. So the only way that can possibly converge is if eventually I am effectively just adding zeros, which means the sequence needs to have a limit of zero. So basically the divergence theorem says this: if that limit is anything else, or if it just doesn't exist, then your series can't possibly converge. So this sequence here, it diverges by, I can say divergence theorem or alternating series test. Any questions on this one? All right, let's keep on going. How about this one here? What do we think about this one? Does it converge or diverge?
Diverge.
Got to vote for diverge. Anybody else? So let's look at it. Can I use the alternating series test? So let's start checking off the boxes. What's one of the conditions I need for the alternating series test?
That it's positive.
That what's positive?
B sub n is positive.
Okay. So in this case, what is B sub n? And really, let's get both. What's B sub n equal to?
N squared over 3n plus 1.
All right, so let's check both those boxes. Is this non-alternating component, is it positive?
Yes.
Yep, that's true. What's the other thing that it has to be?
Decreasing.
decreasing. Do we think that's true?
Yeah.
So those are both verified. What else do we need to look for? So it's called the alternating series test. So what do I need to make sure happens?
For a sub n to be -1 to the power of n plus 1.
Yep. So yeah, and really I just need it to be alternating. So those are my three criteria to use this thing. So yes, I can use the alternating series test. So I'll let you keep going with this. I am allowed to use the alternating series test. So how do I use it? How do I proceed from here?
Look at the limit of b sub n.
Good. So as n approaches infinity, what does this do? So what is this limit? Or someone give me a good next step to start looking at this limit.
Would you use geometric?
No, it's not going to be geometric. So one thing this has come up a couple times. They look similar, but pay attention to these differences. If I have n to the third power or 3 to the n power, only one of these is geometric. And it's really all about, so this one right here is geometric. This one right here is not. And it's really all a matter of basically, where's your variable? In the left, I have a variable base and a constant exponent. On the right, I have a variable exponent and a constant base. And only that situation is geometric. So I can't use geometric. Yeah, I can't think about this as a geometric series, but keep in mind, I'm really only looking at the limit of the sequence, not the series. So there's kind of a way to manipulate this n squared over n cubed plus 1 to maybe look at the limit more easily. But that's not the only way we can do it. Is there anything else we can look at? So hopefully you're noticing that as n gets very large, numerator is going to increase without bound, denominator is going to increase without bound. So a couple ways we can go at this. I'm going to divide both top and bottom by divide both numerator and denominator by n cubed. And then I get to trade that limit for this one. 1 over n divided by 1 plus 1 over n cubed, which is equal to 0 over 1 plus 0, which is equal to 1. Or from what I've seen on quizzes and things like that, I'm guessing a lot of you would like to do this L'Hopital's rule approach, which you can definitely do. So this gives me this limit, 2x over 3x squared which instead of doing L'Hopital's rule again, I could just simplify. I don't know why you all let me get away with 0 over 1 being 1. So that limit is 0. So what does that mean about my alternating series?
Converges.
It converges. So yeah, I met all the conditions, and the non-alternating part of that sequence goes to 0. Any questions there? All right, let's keep on going. How about this one? All right. So I'll let you direct me where to go with this.
So it B sub n is positive.
So what is B sub n?
That would be the square root of n over n plus 4.
All right. So you're saying this is positive, which I agree with. Right, so that's a good start. What else do we know?
It would be decreasing too.
Yep, I agree with that. All right. Good. So we're starting to, check off some of the boxes for alternating series tests. Have I gotten them all, or do I need to keep investigating?
And it would be alternating.
Okay, and what's my alternating component?
The -1 to the n minus 3.
Now, maybe it's not totally important to realize this, but maybe you've noticed that these two things are exactly the same. And the reason for that is this. Basically, what I can do here is kind of factor out a -1 to the power of 2. And -1 squared is just +1, so if it's not obvious that n minus 3 power doesn't really change anything in terms of the alternation, there's another way to show that. So it's alternating, it's positive, and it's decreasing. All right, so we can use alternating series test. So then what do I do?
You look at the limit of B sub n.
So as n approaches infinity, what does this do? So how do I evaluate that?
Isn't because there's a higher power n in the denominator, it would approach 0?
Yeah, that's
Or is that
essentially
not
what's going to
fair to say?
happen. Yeah, that's basically what's going to happen. And if I haven't made it clear, the kind of this manipulation I keep doing, what do I want to divide both sides by here? Or I want to multiply both numerator and denominator by 1 over what? More importantly, how do I make that choice?
Would it be by n?
Yeah, by n. And do you know why, Jacob?
Because it's the larger one?
Yeah, it's the basically I want the largest power of it. Because really when I evaluate this limit, what I want is I don't want any positive powers of n. Because then that way I can evaluate the limits really in a really straightforward way. So this power of n is going to be -1/2. The n is going to become 1. And this is going to become 4 over n. So basically, now the largest power of n that I have is 0. And since I'm letting n go to infinity, all these limits are going to be finite. So 0 over 1 plus 0 is 0 again. So what does that mean about this series?
It would converge.
It converges. But just to kind of relate it to things we've done, what if instead I showed you this series? What does this series do?
You use direct comparison, right?
I don't know if direct comparison would work, but limit comparison certainly would. What's a good series to compare this to?
You do 1 over n?
1 over
Or-
n is not probably going to, but 1 over radical n would be good. And I'll show that briefly why. Let's say I want to do limit comparison. I'm actually kind of glad this came up because this will show why. I'll get there. I'll get there, then I'll explain what I was shooting for. So if I wanted to compare radical n over n plus 4 to 1 over n, then this limit would be equal to n to the 3 halves over n plus 4. Keep doing that. And that right there would blow up to infinity. So what I really want to do, and it's all, I want to compare it to something that's going to more closely give me the difference between, highest power of the numerator and highest power of the denominator. So this, if I rewrite this, n equals 1 to infinity, n to the 1/2 over n to the 1 plus 4. Hopefully it's clear that's going to trend toward n to the 1/2. So if I take this limit instead, That's going to be equal to this limit of n over n plus 4, which that goes to 1. So that tells me that both these series do the same thing. And what do I know that this series does? Does that converge or diverge?
That one diverges.
Divergence. So this is another one of those cases, kind of like the first one we saw, where you can have a series. I'll just go ahead and box in the one that we were really talking about. This is kind of a tangent, but you know, this series converges, but if you take the alternation out of it, it doesn't. So this is kind of another example where, you know, the sequence going to 0 is not enough to tell you that a series diverges or a series converges. I think this is going to be the last one, so let's go ahead and finish up with this one. So I want to know if this series converges or diverges. So how would I go after this one?
B sub n would it be 1 over square root n?
So yeah, my non-alternating part, this definitely doesn't alternate. So does this alternate?
It would, wouldn't it?
Yeah, it does. And I mean, this is one of those, sometimes you'll see this, it's a little more rare, but this right here does alternate. And really think about what cosine does at multiples of pi. Cosine of 2 pi is +1. Cosine of 3 pi is -1. And it's just it'll alternate indefinitely like that. So by far, the more common way to show alternation is -1 to some power, but this definitely works too. So we got the alternating part. What else do we need to show?
That it's positive.
Okay, and is it?
Yeah.
Absolutely. And finally,
That it's decreasing.
all right, and is that true?
Yeah.
Yeah. So we can use alternating series tests. And what is that alternating series test going to tell us about this series?
If it converges or diverges.
Yeah. So what do we need to look at?
The limit of Bn.
So the limit as n goes to infinity of 1 over radical n is equal to what?
0.
0. So this series does what?
It would converge.
Yep, converges again. All right. Any questions on alternating series, that test? So what else we did tonight? So we did a alternating series test. We did limit comparison, direct comparison, and integral test. So any questions about when you're allowed to use those, how to use them, anything at all? Okay, what time do I have? 8:50. Yeah, but I don't want to start anything new, rather just get into it fresh tomorrow. So I am going to stay online for the next 20 minutes until 9:10. Very shortly, I'm going to upload the quiz for tonight. And the slides. So keep an eye out for that. The quiz will be due as usual, 5 o'clock tomorrow afternoon. But if you don't have any questions for me, you're free to go, and I will see you tomorrow evening.